Hey everyone, today we're going to talk about exponential functions. Exponential functions are functions that change as a given percentage over time. Unlike linear functions, exponential functions grow faster or slower over time. Sometimes an exponential function looks like half a quadratic. The big difference is that an exponential function has an asymptote. If you're given data, ask yourself, will this change directions or get closer to an asymptote? I'll show you what that means in a minute. Growth or decay. Exponential functions can either be growth or decay. Both are examples of exponential functions, and they have similarities and differences. They both have a y-intercept at an initial starting value. They both have 0 as an asymptote, and they both decay or grow as a fixed percentage, not as a slope. But growth numbers increase, where decay functions decrease. Growth functions' asymptote is on the left side, where decay functions have an asymptote on the right side. Visually, growth functions look like this, with the asymptote over here. This is growth. It's growing. Decay functions look like this, the asymptote on the right side. They're going down and getting closer and closer to some bottom number. What about as an equation? They look like this, a parentheses b to the x power. A is the starting value, or the x-intercept. Or the y-intercept. B is the percent remaining after each trial, and we'll use that to find the growth or decay rate. The growth or decay rate is b minus 1, and we'll show you what that means in a second. To determine if it's growth or decay, look at b. If the value is larger than 1, it's growing. If it's less than 1, it's decay. For example, the b here is 1.23. So it's growing, it's bigger than 1. 1.23 minus 1 is 0.23, or 23%. This function is growing at a rate of 23% per year, day, month, week, whatever we're talking about. Take a look at this one. 0.59 is less than 1, so it's decay. 0.59 minus 1 is negative 0.41, or 41%. I'm losing value. So I'm decaying at 41% per year, day, month, week, whatever. So talk to me. What are the starting value and the growth and decay rate? So for the first one, its starting value is 2. It's bigger than 1, so it's growth. By how much? 1.35 minus 1 is 35%. It's growing at 35%. For the second one, it starts at 3.5. It's decaying. How fast? Well, 0.72 minus 1 is negative 18%. It's negative because it's decaying. I'm losing 18%. The third one people have trouble with. The starting value is 5. It's growth because it's bigger than 1. How much is it growing? 3 minus 1 is 2, or 200%. It's tripling every time. How do we use this to model real-world behavior? Exponential functions are some of the most common functions used in the real world. Anytime you use a percentage to get the next value, you're using an exponential function. Common examples of growth are bank savings accounts, populations, values of antiques or collectibles, decay, credit card debt, mortgages, vehicle trade-in values, amount of medicine in the system. We're going to determine if it's growth or decay. So we're going to have to read and use a little bit of common sense. Identify what we know, whether we know the growth or decay rate, the starting value, the time interval, or the final amount. Set up an equation. The equation is the final amount equals the starting amount, 1 plus the growth or decay raised to the time interval. And then use a calculator, find for the missing information. What if you need to solve Graph both sides and then find the intersection. Example. Your parents buy a CD at your birth for $1,000. The bank promises a return of 5.65% on the investment. How much will the CD be worth when you turn 18? So what do we know? How much do we start with? 1,000. What's my growth or decay rate? I'm growing at 5.65%. How long? 18. Final amount? I don't know. So my equation is y equals 1,000. 1 plus, not 5.65. I need to turn it back into a decimal. 0.565 raised to the 18th power. That one's really easy. I'm just going to plug it in the calculator, and I'm going to do it myself and tell you the answer is $2,689.37. Start with 1,000. I grow at 5.65%, so that's 0.0565 raised to the 18th for 18 years. $2,689.37. You have bought a new iPhone. However, the value of the phone depreciates at a rate of 13% per month. Suppose that you sign a 2-year contract. What will your trade-in value on your phone be at the end of your contract? Well, it doesn't tell us, so I'm going to make up a number. Let's say that your phone costs $700. And that's about right for an iPhone. So starting amount, $700. Decay, it's losing 13% per month. That's 0.13. For how long? 2 years. But it's 13% per month over 2 years. So that's 24 months. And I don't know the final amount. So the final amount is the starting amount of $700, 1 minus 0.13 raised to the 24. Minus because it's decaying. Plug that in your calculator and see what you get. And it's very depressing. Your $700 phone now is worth $24.75. Isn't that sad? Your bank or your broker promises that your investment will grow at a rate of 9.5% per year. You decide to invest $2,000. How long until your investment is worth $10,000? This one's different. Start with $2,000. End with $10,000. You're growing at 9.5% or 0.095, but you don't know how long the time interval is. So the final amount, 10,000, I don't know why I put 1,000, equals 2,000, 1 plus 0.095 raised to the x power. Now how do I solve any equation? Well, I plug in the calculator and set each side equal to each other. The first thing I'm going to do, make this problem a little bit easier, is I'm going to divide both sides by 2,000. That tells me that 5 equals 1.095 to the x. Now I'm going to grab a calculator. I'm going to put this side in y1, this side in y2. Y equals, the left side is 5, and the right side is 1.095 raised to the x power. And I'm going to graph it. They don't cross yet, so I have to zoom out, enter. Now they cross. Second trace 5, enter, enter, enter. How long does it take? 17.734 years. It's not bad. How do I graph these? Well, I'm going to determine the y-intercept. That's the same as the starting value. I'm going to determine whether it's growth or decay. I'm going to plot the y-intercept, and I'm going to graph at least one point on either side, and I'm going to use the calculator to help, and then I'm going to sketch the graph. And be sure to include the dotted line as an asymptote. So, what's my y-intercept in this problem? It's 2. Is it growth or decay? It's growth. It's bigger than 1. So I know I have an asymptote right here. And I know my y-intercept is 2. And if I just want to sketch a basic graph and not use exact points, I'm just going to draw it like this. It's growing. What's the domain? Well, it goes left and right forever, so it's all real numbers. What's the range? 0 to infinity, because the bottom is 0, but it doesn't touch 0, so I can't include 0. It's parentheses. How about this one? Your y-intercept is 5. It's decay because it's less than 1. So I put a dotted 5 and an asymptote. And then I sketch a decay graph going down. What's my domain? It's still all real numbers. What's my range? Still 0 to infinity. Still the bottom is 0 and the top goes up forever. Don't forget about all your transformations. They all hold true. Left and right, up and down, reflect. And you don't need to worry about shrink or stretch since the A value already takes care of that for you. If you forget these, feel free to pause and look over them, but I'm going to keep going. Sketch this. I'm going to sketch the original graph. The original graph has a y-intercept at 8, an asymptote at 0, and it's 0.7, so it's decay. But what transformations have happened to this thing? It went down 3. So now my y-intercept is right here, my asymptote is down 3, and this is my new graph. What's the y-intercept? It used to be 8, now it's only 5. It's still decay. The domain is still all real numbers. All exponentials will be all real numbers. But now instead of going from 0 to infinity, since it went down 3, it's negative 3 to infinity. And that's it, guys. Thank you very much. If you have any questions, come talk to me.